Alright, welcome to Projectile Motion for Chapter 13.2. And in this video, I'm going to go over one simple, one relatively harder example of projectile motion problems that we'll see. And the first question I'm just going to preempt is a lot of students ask, oh, can I just solve projectile motion problems with physics? And yeah, duh, of course you can. That's what projectile motion is. It's essentially a physics application of position vectors, tangent vectors, and acceleration vectors. So we got position, velocity, acceleration, which are all just derivatives of one another, and that's the whole point of this chapter. It's just some application of what we learned in 13.1. Okay, and so this first problem then is a bit of a frivolous problem. It comes from the final from fall 2008. It talks about President Bush, right? So I don't know how young you guys were when you guys watched this are watching this video, or how you guys were when Bush was president. But yeah, so during a Bush conference in Iraq, I think, some dude tossed a shoe at President Bush, and this problem is making fun of that. So this problem, okay, so an Iraqi reporter throws a shoe at President Bush during the president's last press conference in Baghdad. All right, the report is a horizontal distance of 12 feet. Okay, so here's the diagram. He's 12 feet from the president and launches a shoe with initial speed of 24. Okay, so you see the vector with the shoe going at 24 feet per second. And then it's 45 degrees from the horizontal. And it's 3 feet above the ground, which is how high the guy was tossed it initially. All right, and then at liftoff, okay, got that. And then there's an acceleration constant, which is g is equal to 32 feet per second. Cool. So we want to find then how high the shoe will be when it reaches President Bush, which is this guy. He's President Bush, whatever. Yeah, so how high will the shoe be when it reaches President Bush? And so our question here then is, for projectile motion problems, we have 4 equations that we like to use a lot. The first one is just then R of t, which is the position equation for projectile motion. So given a time and then all these other variables, right, I can see at what position is my projectile going to be, right? And then these other 3 equations down here are all assuming, I said flat ground, but maybe a better way to phrase it is that your object lands at the same height it was thrown at, okay? So if you can guarantee that an object is landing the same height it's thrown at, then you can use these 3 equations, which are really nice and really helpful, okay? The first one talks about the maximum height the object's going to reach, call that y max, and it's given there. Equation 3 talks about the total time it takes for an object to get launched and then land at the same height, okay? So that's t total, the total time. And the last one, 4, is range, is how far does this object travel in total, okay? So from it being thrown and from when it lands, how far did this object go? Okay, so, well, we can't really use these last 3 equations for this problem, right? Because we don't even know what the height is at time equals 12. So these last 3 equations aren't very useful for us. And so that means we're going to have to use this first equation, which is the projectile motion equation. And let's see what it is. So the projectile motion equation in this problem is R of t is going to be equal to, all right, v naught t cosine theta is 24 cosine theta is root 2 over 2, right, t, all right? And then you got negative 1/2 times gt squared, so 32t squared, right, plus v naught sine t, well, that's 24 sine of 45 degrees, which is still root 2 over 2. And then you got t, right, so this is sine of 45 degrees, and that's v naught. And then you got plus initial height, which is 3, okay? And what do I want to know? Well, it'd be useful, right, since I'm essentially trying to find the position of the shoe, okay, when the x-coordinate is 12. So I want to find the position of the shoe when the x-coordinate is 12. And how can I do that? Well, I probably want to find what t is going to be in order to get x equals 12, right? So I want to find t such that the x-coordinate is 12. All right, because again, my position of my shoe is at 12 comma something, right? And if I find t, then I can just plug in t into this guy and find the y-coordinate, which is the question mark right now. So let's find t. So I know that, well, what's 24 times root 2 over 2? That's 12 root 2t is equal to 12, right? This is the x-coord. And so t then is going to be equal to 12 over 12 root 2, which is the same thing as root 2 over 2, okay? And now what I can do then is plug in root 2 over 2 into this equation. And so doing that, r at root 2 over 2, the y-coordinate is going to be, so this is negative 16 times root 2 over 2 squared, okay, plus 24 times root 2 over 2 times root 2 over 2, or, well, 24 times root 2 over 2 is 12 root 2, okay, and then plus 3, right? And what is this? Well, root 2 over 2 squared is 1/2, right, because you get 2 over 4. So I get negative 16 times 1/2, that's negative 8, plus 12 root 2 times root 2 over 2. So 12 and 2 cancel, that's 6. And then root 2 times root 2 is 2, so I got 6 times 2, that's 12. And then I add 3, okay, and that means my final height is going to be 7 feet, right? The final height, the y-coordinate of this shoe toss is going to be at 12, comma 7. All right, and that's what we found. So the answer is going to be E for this first problem, okay? And again, we use this number 1. And this is going to be a theme for a lot of these problems, is that you're going to have to use the x-coordinate to find a time, and then you plug that time into the position equation to find the y-coordinate. Got it? Cool. What's the next question? All right, the next question now is from fall 2014, or spring 2014, and it's the following problem. A ball is thrown at ground level, and after 5 seconds, it lands 10 meters away. What was its initial speed? The gravitational constant is 10 meters per second squared. Okay, and looking at this problem then, it doesn't say anything about an initial height or an uneven surface, so that means we can probably use one of these other equations right here, right, to help us. Well, what do we want to find, right? We want to find the initial speed. Okay? What do we know? We know that t equals 5, all right, is the total time, all right, t total is 5, right, because that's what it says, right, after 5 seconds, all right, it lands 10 meters away, so that also tells me then the range is equal to 10, okay, and we also know that g is equal to 10 meters per second. Okay, so given t total and a range, we probably want to play with those two formulas, right? So what's the formula for t total? It's 2v naught sine theta over g, and range is v naught squared 2 theta over g. So let's write those down here. So I got t total is equal to 2v naught sine theta over g, but we know what g is, right? G is 10, so let's just put in 10, okay? And what is range? Well, range is going to be v naught squared sine 2 theta over g, but again, g is 10, so let's just put that in there, all right? And what is t total? Well, t total is equal to 5, and range is equal to 10. Okay? We're cool with that? Great. So how do we do this? Well, okay, what do we want to find? Let's think about this for a second. If I want to find, I want to find v0, right? I want to find v0. So if I have an object, and it gets tossed, right, at some initial v0, right, it's really going to look something like this, right, because of the force of gravity acting upon it, and it's going to land somewhere here, right? But it makes sense then. I can find the initial speed if I complete my triangle here, right? So I can take this part, which is v naught cosine theta, right, and this part, which is v naught sine theta, and I can simply use the Pythagorean theorem, right, to find what v is, because then I could get v naught is really the square root of v naught cosine theta squared plus v naught sine theta squared, right? And that makes sense because if you actually work this out, you get v naught squared cosine squared theta plus v naught squared sine squared theta. You can factor out the v naught squared. You get a cosine theta squared plus sine squared theta, or cosine squared theta plus sine squared theta, which equals 1, and then you take the square root of the remaining guy, which is v naught, right? So this is actually a true statement right here. So what I can actually find then is I can actually just try to find a v naught cosine theta, and I can find a v naught sine theta, and use this relationship right here to help me find v naught, or the initial speed, okay? So I don't actually have to work to find, you know, the launch angle and all that BS, right? I can just simply look for v naught cosine theta and v naught sine theta. Okay, so how are we going to do this? Well, from these two equations given to me right now, there does not seem to be both a v naught cosine theta and a v naught sine theta, right? We have a v naught sine theta right here, okay, that we can solve for, which is good, right? Because if I know what v naught sine theta is, all I need to do is figure out what v naught cosine theta is, plug it into this equation, and get myself a v naught. But we don't know what v naught cosine theta is. So I encourage you guys to pause this video, and from these two equations, try to figure out where in the world can I get out a v naught sine theta, okay? So pause the video, think about it for a second, and see how in the world can I introduce a v naught cosine theta, because I have a v naught sine theta, I need a v naught cosine theta. All right, so if you thought about it or if you gave up, it's perfectly fine. Where in the world can we find a v naught cosine theta? Well, here with the 2 theta, we're going to have a v naught cosine theta, right? Because we have sine of 2 theta. And we know from high school trig class that sine of 2 theta is equal to 2 cosine theta sine theta, right? Cosine, or sine, cosine, cosine, sine, right? You add them together. So that's what sine 2 theta is. So this is actually v naught squared times 2 cosine theta sine theta over 10 is equal to 10, right? And what's more is that, all right, let's actually simplify this now. This is really, right, v naught squared cos theta sine theta over 5 is equal to 10, right, by dividing the 2. And since this is a v naught squared, I can have a v naught cosine theta times a v naught sine theta over 5 is equal to 10, right? So that's because v naught times v naught gets me this v naught squared, and then here's the cosine and there's the sine, right? So perfectly fine. And so this is how we introduce then a v naught cosine theta into the equation, okay? And so from above, from this first guy, t total, we can actually solve for v naught sine theta, right? So v naught sine theta is equal to 5 times 10, right? Multiply by 10 from both sides, divided by 2, right? And then that's equal to 25, right? So I took 10, multiplied it on both sides, and then divided both sides of this equation by 2, right? And then I get v naught sine theta by itself, which is 25. Great. So I found what v naught sine theta is. It's 25. Now, let's use this info and plug it down here. And now I got v naught cosine theta times 25 divided by 5 is equal to 10, right? And solving for v naught cosine theta, I get v naught cosine theta is equal to 2. All right? So now I have v naught sine theta, I have v naught cosine theta, and that means I just need to plug it into this equation up here. V naught is equal to v naught cosine theta plus v naught sine theta, v naught cosine theta squared plus v naught sine theta squared, and take the square root of that. So v naught is equal to the square root of v naught cosine theta squared, which in our case was 2, right? So it's 2 squared plus v naught sine theta squared, which in our case is 25 squared, and we see now that the initial speed is going to be the square root of 629. So these are the kind of projectile motion equations you'll see. In my recitations, I'm actually going to teach you guys how to construct the projectile motion equation from scratch, from just the acceleration vector, and that's because that's very necessary to do three-dimensional projectile motion problems, which doesn't really show up. I think I've only seen it once. I can't really find it again. So yeah, and this is like the essence of a projectile motion problem. You gotta fool around with the formulas. You gotta know what you want, and you gotta be able to find you want to manipulate these equations in certain ways to get what you want. Okay, so that's it for projectile motion. Next one is arc length. Short video on arc length, and then we'll keep chugging along in this textbook.